Okay, so I'd like to tell you about the tropical garden. So a tropical garden, of course, has many trees. It has other beautiful flowers and objects that I'd like to share with you. You can find a real tropical garden if you cross the Expo Bridge. So if you cross the Expo Bridge that looks like the McDonald's arches, you go a little further and then you make a left turn, there's a real tropical garden. So if you don't like my tropical garden, or even if you do, you can go there. So this is chapter 5 in the forthcoming book. This is from chapter 5 in the forthcoming book on tropical geometry with Diane McLagan. And I'd like to start out by telling you about eigenvalues and eigenvectors of square matrices, n by n matrices. Suppose you run an airport. And the airport has regularly scheduled flights throughout the day to various cities. And there are n gates in the airport. And you like to run your airport as efficiently as possible. So let's say there's a time, so people come in one gate I, and they leave in another gate J. And it takes them a certain amount of time, Aij, to go from gate I to gate J. Okay, there's a certain lag time. That's a positive number. And what you like to do is you like to schedule regularly the flights to come in. They all come in at various offset times at these gates. Everybody gets off their gate, collects themselves, walks to the next gate. Okay? And then all flights take off again. Okay? Suppose you want to organize that in such a way that you can process, as many flights as possible. How should you do that? That's a typical scheduling problem, and that's what I just described is in fact equivalent to the eigenvalue problem for an n by n matrix over the tropical semiring. So we're going to work over the real numbers together with maybe plus infinity. We're going to work in the min plus algebra, so the sum of two numbers, the tropical sum, is the minimum, so 3 plus 5 is 3, and the tropical product is the classical sum, 3 times 5 is 8. And I'm going to state a theorem right away. That's theorem Fun 511 in this book, which is in draft form available on my website. So let A be a matrix. I'm going to say a tropical n by n matrix. Tropical matrix. So tropical just means the entries are real numbers, but I do allow plus infinity. So maybe it's impossible to go from some gate to some other gate. Okay. However, the graph of this matrix, G of A, should be strongly connected. So what do I mean by the graph? Well, that's a directed graph on n nodes. And, there's a node I, there's an edge from I to j if and only if the entry is not plus infinity. Right? So there's an edge from node I to node j, and we label that edge by the matrix entry Aij. Okay? So we're identifying matrices, n by n matrices with weighted directed graphs on n nodes. And strongly connected means that between any ordered pair of nodes, so node I and node j, say gate I and gate j, there is a directed path from I to j. Okay? So let me assume that my matrix, so in particular, if in the matrix there's no plus infinity, if it's just a real matrix, then trivially it's strongly connected. Okay? The statement is that our matrix has precisely one eigenvalue. Every n by n matrix has precisely one eigenvalue, exactly one eigenvalue, and that eigenvalue equals, tell you what it is, it's equal to the minimal normalized length, classical length, of any directed cycle in the graph.
missed the definition of strongly connected.
Okay, so a directed graph is strongly connected if between any two nodes, node I and node J, there's a sequence of directed edges that starts at I and ends at J. Okay, so for example, you could have a graph like this. So this directed graph is connected, but it's not strongly connected because you can never go back to this sink. But if we introduce one more edge like this, now it's also strongly connected. Strongly connected in the directed sense. We can go from any city to any other city by a directed sequence of edges. Okay, so this is the theorem. Okay, so let's see an example. So here is a 4 by 4 matrix. So 4, 5, 3, 3, 3, 5, 4, 6, 6, 1, 5, 3, 5, 5, 2, 5. Okay, so this is an n by n matrix, 4 by 4 matrix. So the claim is there's exactly one eigenvalue. Well, that's I claim the eigenvalue lambda of A. Let's put it here. So lambda of A is equal to 9 over 4. Okay, so I claim that the eigenvalue is 2.25, 9 quarters. And here is an eigenvector that realizes this eigenvalue. So 3 quarters. I'm going to write this as rational numbers. 3 over 2, 1 quarter, 0. Okay? So, you check, right? So let's check. So A times X in tropical arithmetic, right? That's a matrix times a column vector. That's a column vector. I claim that that's lambda, scalar multiple X. So let's take a moment to check this, right? So for example, let's do this in the first coordinate, okay? So, for example, 3 times 0 is 3. 3 times a quarter is bigger than 3. 5 times this is bigger than 3. 4 times this is bigger than 3. Okay? So this product in the first coordinate is 3. Okay? But 9 quarters times 3 quarters is 3. Okay? So we checked it in the first coordinate. Okay? Some people still look puzzled. Okay? So Kangjin, are you okay? Should we do in the last coordinate? Okay? So let's do the last coordinate. So I claim this guy is let me mark the winner. Okay? So the winner here, that was the last entry. So I claim, I did this before, okay? So I claim 2 is going to be the winner, okay? So 2 times a quarter, 2 times a quarter, that's 9 quarters. Okay? That has a chance, right? Because 0 times 9 quarters is 9 quarters. But everything else is bigger. So 5 times this is bigger than 9 quarters. 5 times that is been that 5 times that is also. So it's also okay in the last coordinate. Okay, so if we take our matrix, we multiply it tropically with the column vector x, we get 9 quarters tropically scalar multiplied that same vector. So we say that x is an eigenvector of this matrix. I'm going to say lambda is an eigenvalue, but according to this theorem, it's the eigenvalue because there's only one eigenvalue. Okay. Now the other part is that's the normalized length of the optimal normalized length of the cycle. So let me exhibit for you the optimal cycle. So the optimal cycle in this case that minimizes. So by normalized length is I travel along a directed cycle in my graph, and I classically add the edge lengths and I divide by the number of steps I took. Okay. So I first go from gate 1 to gate 4, that's length 3. Then I go from 4 to 3, that's length 2. Then I go from 3 to 2, that's 1 step, and then I go from 2 to 1, that's 3 steps. So I classically add these numbers, 3 plus 3 plus 1 plus 2, that's 9 classically. I divide by 4, and that's the 9/4. Okay, so that cycle realizes the normalized cycle length, and every other cycle is longer. So this includes the 1-by-1 cycles. For example, every diagonal entry is a cycle all by itself, right? So this corresponds to a loop from gate 4. You just stay at gate 4, and it's a loop from 4 to 4. The normalized length is 5. Okay, let's do another one. Let's say you go from gate 3 to gate 4 and back, right? Then the normalized length is 5 over 2, and that's bigger than 9 over 4. Agreed? Okay, so among all cycles in this directed graph, all cycles of either length 1 or 2 or 3 or 4, if we look at the normalized cycle length, 9/4 is the winner. And that is the eigenvalue of this matrix. Okay, now it looks like, so how can you compute this? What's a good way of computing this eigenvalue? It looks like there are exponentially many cycles. There are lots and lots and lots of cycles, but there's a nice efficient polynomial time algorithm for finding the eigenvalue. So this is proposition 512. So this is Dick Karp, very senior theoretical computer scientist, now the director of the Simons Institute for the Theory of Computing in Berkeley. So Dick Karp, 30-some years ago, looked at this minimal cycle problem, and he showed that this number is the optimal value. Is the optimal value gamma star of a classical linear program. Classical linear program. We're going to get to tropical linear programs a little later. This is a classical linear program, and the classical linear program is to maximize, just maximize gamma subject to a very simple linear system, namely A times X, X is a vector of unknowns, times gamma X. Okay, so let's unravel this. So if you look at this system of inequalities, okay, so A is fixed and given. This translates into a classical system of n linear inequalities and n plus 1 unknowns, right? So the decision variables are x1, x2, up to xn, and gamma. So the n plus 1 decision variables. And then if you unravel this classically, these are linear inequalities, okay? So what this says is we're looking for the largest sub-eigenvector. So this inequality, so if gamma and lambda, the largest sub-eigenvalue. So if this inequality holds, we say gamma is a sub-eigenvalue and x is a sub-eigenvector, and then this problem is equivalent to maximizing the largest sub-eigenvalue that will automatically be the largest eigenvalue. Exactly the eigenvalue. Okay, and this is a very, very efficient method for calculating the gamma. Now, why are we doing today what we're doing? This course, after all, is supposed to be about non-linear algebra, extensions of linear algebra. And I was extremely happy to see that on your Google Scholar page, you cite your area. You're the only person known to Google Scholar right now to have as the area non-linear algebra. So welcome to be the first. I will join you. I will be the second, I think. So non-linear algebra is a field as of recently on Google Scholar. But on the way to non-linear algebra, today we're doing a little bit of piecewise linear algebra. So there are many ways to get from linear algebra to non-linear algebra. One route is by way of a multilinear algebra. But today we're going to go by way of piecewise linear algebra. This is to say tropical algebra. Okay, so there's our proposition. Now let's talk a little bit about the eigenspace. Now the eigenspace is unique, right? So there's only one eigenvalue. So then, yes, question?
I have a question on this side. You said this is LP, the classical LP. I can see how to formulate it on the left-hand side, but I don't know what.
Okay, let's see this. Let's look at the first coordinate, okay, and write it classically. So that's the minimum of a11 plus x1, and a12 plus x2, and a13 plus x3. Okay? So the minimum of a bunch of linear expressions, aij plus xj, should be greater or equal to gamma plus xi. So the minimum of a bunch of, so this really, I'm sorry, this is n squared linear inequalities, right? Because we're taking the minimum. So there's a system of n squared, very simple linear inequalities in n plus 1 unknowns. So each inequality says that aij plus xj is greater or equal to gamma plus xi. Is that clear? Other questions? Okay, n squared, it's a very, very simple linear program. That makes it very, very fast. So if you try this, this runs in no time, I mean, even on fairly large matrices. Okay? Okay, let's talk a little bit about the eigenspace. Now there's a unique eigenspace. So we're going to identify the eigenspace. So what's the eigenspace? I noted Eig of A. So by the eigenspace of a matrix, I'm going to mean this set of all eigenvectors. And of course, these eigenvectors now are going to use all the same eigenvalue, right? So that's Ax equal lambda of A times x. Okay, so this is the eigenspace, the set of all eigenvectors that work for the eigenvalue. Well, we're going to identify it with its image in Rn modulo the subspace, classical linear subspace spanned by the all one vector. Okay? Well, that's very natural, right? Because this corresponds to scalar multiplication. So classically, if you have an eigenvector in linear algebra and you multiply it by a scalar, it's still an eigenvector. Right? Same here, except that it's tropical scalar multiplication. So if you take an eigenvector and you tropically scalar multiply it with a number, you still have an eigenvector. But tropical scalar multiplication is classical scalar addition, and that is to say shifting, by the all one vector. So for example, if we multiply, this thing by a quarter tropically, so we get 1, 3/4, a half, a quarter, right? It's still an eigenvector. So we might as well work modulo 1, 1, 1. Okay? So we can think about this as an n-1 dimensional affine space. It's a good idea to think about this as tropical projective n-1 space, right? So projective space is really an n-dimensional vector space, and you mod out by scalar multiplication. Two vectors are the same if they differ by a scalar, one is obtained from the other by scalar multiplication. And in many early papers on tropical geometry, these were considered equal. So in my early papers on tropical geometry, I defined this to be tropical projective space. But just to show you that I'm not as stubborn as I may appear, I changed my mind. So McCulkin, McLagan, all my friends convinced me that projective space should really be compact, right? So you can have an intersection theory. But for the purpose of this discussion, combinatorial discussion, we might as well think about this as tropical projective space, okay? So if I draw pictures of this eigenspace, I work modulo the 1, 1, 1 space, or equivalently, I'm always going to assume that the last coordinate is 0. Okay, so that's what we're going to do. So to compute this eigenspace, let's introduce a new matrix, B. So let's take minus lambda A, that's classical subtraction. So I take the negative of my eigenvalue and I multiply the matrix by A. Okay? That's a new matrix B. So this says I take my matrix and I classically subtract 9/4 from every entry. Okay? So this is, so if I do that, that's scalar multiplication. Let's remember what happens to square matrix, right? So if you have a square matrix and you know an eigenvalue, and you multiply that matrix classically by 17, well, then the eigenvalue just, you add 17, right? So that just shifts. I'm sorry, you multiply the eigenvalue. So the effect here is that, so what? So lambda of B is now 0. Okay? So combinatorially, this also makes sense. So we have an optimization problem. We want to find the shortest cycle mean in the directed graph in the United Airlines flight network, right? We want to travel the world on United Airlines. How fun is that? And find the cheapest way to do it, and we normalize that to have cost 0, right? We're subtracting the 9/4 from every edge, okay? But the eigenspace is the same, right? So we didn't change the eigenspace. So we just normalized the eigenvalue. But the set of eigenvectors is still the same. Every eigenvector of B, you just run through the arithmetic. Every eigenvector of A is still an eigenvector of B and vice versa, except the eigenvalue is now normalized to be 0. Okay, so let's spell this out. So we're interested in the set of all eigenvectors, x in Rn, such that Bx is 0 times x, and remember 0 is the multiplicatively neutral element, right? So we're interested in solving the equation Bx equals 0 times x, or equivalently Bx equals x. Okay, so now we're looking for fixed points of B. So in linear algebra, eigenvector computations correspond to fixed points of linear maps. In nonlinear or multilinear algebra, eigenvectors correspond to fixed points of nonlinear maps. Okay, that's a different topic. So here let's talk about Bx equals x. And here's my second theorem that will characterize the eigenvalues, the eigenvectors. Theorem 513. Okay, I'm going to introduce one more matrix I'm going to call C. Okay, let C be the submatrix of B star. Okay, so what's B star? B star is the clean star of B, which by definition is B plus B squared plus B to the n. I'll explain this in a moment. So I'm going to form this matrix by tropical arithmetic. B plus B squared plus B cubed up to B to the n, where n is the size of the matrix, and matrix multiplication and matrix addition are tropical. Given, let me write the sentence and then I'll explain it, by the columns whose diagonal entry B star II, that's the diagonal entry, is 0. The image of C is the desired eigenspace. Okay, so the desired eigenspace of A, which is equal to the eigenspace of B, this fixed points, That's the image of the matrix C, the usually rectangular matrix C that has still n rows, but possibly fewer columns. So let's explain this theorem. Well, first of all, what's B star? So I claim we could add more terms. This is really the geometric series applied to B. So this is the sum over all positive powers of B, but then higher powers of P will no longer contribute, and that comes from our normalization. So think about it for a moment. So we've normalized things so that no directed cycle has negative length. So no directed cycle has negative classical length. There is some cycle, possibly several, but there's at least one cycle that has length 0, and all other cycles have positive length. Okay? Well, what does this matrix do? So if you keep adding up, this calculates in row I and column J, well, this calculates for you, the shortest number of steps from I, so the shortest length, from I to J in your directed graph, the way we set this up. But since there are no negative cycles, you found the way this cannot diverge, right? So this is going to have a minimum, and that minimum is attained after n steps. Okay? So if you want to spend your life, traveling on United Airlines, you only have to take n flights if there are n cities, right? Then you've got attained it. Right? Clear? So there's no negative cycles. There's no way you can further improve this after n steps. But this B star in general will be different from B. So it's some matrix that's coordinate-wise less or equal to the matrix B, right? So for example, you have, suppose you have these 3 gates, right? And then, from the first gate to the second gate, it's, one step, let's say 10 minutes, and from gate 2 to gate 3, it's 20 minutes, but from gate 1 to gate 3, it's 80 minutes, right? Then, you make progress in adding at B squared, because B squared tells you take a detour, right? You can go from gate 1. Some airports are like this, right? So you have to take a shuttle or something, right? So, but after n steps, you're done. You got the clean star, B star, okay? So we calculate, so here's the algorithm for computing the eigenvalue. I told you the eigenvalue algorithm, that's this red box. Then the eigenvector algorithm is we replace A by the matrix B. That's a normalizing condition that finds makes the eigenvalue to be 0. And then we calculate B star by whatever algorithm you learn in your freshman discrete math class at a undergraduate math major program at a leading university. So you do the Dijkstra's algorithm or Floyd-Warshall algorithm. You calculate B star rapidly. Then you look in the square matrix B star along the diagonal. Wherever you see a 0, so all the diagonal entries are non-negative. Are we clear? Right? They are non-negative. If they were negative, then there would be a negative cycle. Can't be negative, right? So all the diagonal entries are non-negative, and you just keep those columns where the entry is 0, and those columns you keep, and you call the matrix C. That matrix C has still n rows, but it might have fewer columns. And then the eigenspace is the image of this matrix. Okay, so the set of all vectors of the form C times something in R to the n. But of course, we're going to do that in one dimension less. Okay, so that's the basics, the very, very basics of tropical spectral theory. Let's do another example. Question?
The image of C under what? Which map?
C is a linear map.
Linear map.
So C is a tropically linear map. So C is a map from, well, so we'll see an example. So let's say C has R columns and n rows. So then C is a tropically linear map from R-dimensional space to n-dimensional space. And the image is exactly what you think it is. It's the set of all values that you get by multiplying by a column vector on the right. Okay, let's do another example where the eigenspace is a little bit more interesting. So here's another one. Let's take A to be this matrix. 1, 4, 4, 6. 1, 1, 1, 2. 4, 2, 1, 3. 6, 3, 6, 4. And in this case, so if A is this matrix, and make sure I got it correct, then the eigenvalue is 1. So in this matrix, it turns out that the one cycles, the loops at gate 1, gate 2, and gate 3, they are the minimum. Okay, there are no cycles of cycle mean less than 1, and there are 3 loops that attain it. So that makes for an interesting eigenspace. So in this case, the eigenspace of A is the image of the following matrix. I'm not going to go through the calculations. I mean, this is easy to do. So when you have the matrix C, what we usually do is we make the last column 0, right? So for example, if the last entry, you make it 0. Last row is all 0. So if you have an entry in the last row that's 6, you tropically multiply that column by -6, and then it's 0. It doesn't change the image of the matrix, okay? So we can do this -2, -2, -1, 0, 1, -2, -1, 0, 1, -2, -2, 0. Okay, so by the image, I mean, well, all vectors in R⁴ that are tropical linear combinations of the 3 columns. Right? So that's how matrix multiplication works. Okay. So the question I would like to address in the second hour today is how to draw this. How would you actually draw this? Okay. Well, of course, what do we mean by drawing this? Well, we're drawing this in 3 space, right? So this is in 3-dimensional space, right? So this matrix is a linear map, tropical linear map from R3 to R4, or projectively, people who study projective geometry, it's a map tropically from the projective plane P2 into projective 3 space P3, and we want to draw it. We will draw it. Okay? We will draw it. So how would you draw this, right? So this is a vector in 3-dimensional space, the point in 3 space. That's a point in 3 space. That's a point in 3 space, here and there, right? And now we take the set of all tropical linear combinations. Okay? So how would you draw that? And we'll practice this by some flowery, colorful pictures. Okay. Let me end this discussion on eigenvalues and eigenvectors with one more corollary. That's corollary 515. Actually, let's do it like this. So, well, you know, people sometimes wonder what's the relationship of the eigenvalue with the roots of the characteristic polynomial. Right? So in classical linear algebra, we know that with the matrix you have a characteristic polynomial and maybe a minimal polynomial, and the roots of that are exactly the eigenvalues. That's not quite true here, but almost. So the correct statement here is that the eigenvalue of a square matrix, lambda of A, is the smallest root. Is the smallest root of the tropical characteristic polynomial of that matrix. Well, what's the characteristic polynomial? Okay, so it's a polynomial in one variable t, tropical polynomial, so it's the tropical determinant of A plus t times the identity matrix. Okay? Right? So T is an unknown. You multiply the identity matrix with T. You add in A. Right? So it's clear. So for example, let's take this matrix, 2, 3, 5, 7, 11. My favorite matrix. 23 plus T times the identity matrix. The identity matrix is 0, infinity, 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 0, infinity, infinity, 0, infinity.
Oh, the last row.
Oh, last row is messed up, sorry. Okay, and this is tropical. So now, okay, so here we get 2 plus T, whichever is smaller, 3, 5, 7, 11 plus T, whichever is smaller, and then here 23 plus T. Now we take the tropical determinant, right? So the tropical determinant, we know how this goes, right? So this times this times this, plus 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 this times this times that, okay? There's no minus. Well, permanent equals determinant. So that's a tropical polynomial of degree 3 by the Cardano's formula, which the undergraduates learned last Friday, right? So it can be expected to look maybe something like this. There will be 3 roots, and this is the winner, okay? So the largest root, that is the eigenvalue. So the characteristic polynomial, typically here will have 3 roots, or n roots, but only one of them, the largest one, is the eigenvalue. Oh, did I say small? Yeah, I'm sorry. I'm sorry. It's always max versus min. I'm sorry. In the min plus algebra, it's the smallest. I'm getting ahead of myself. So if you use max plus algebra, then you have a more transparent relation to the Perron-Frobenius theory. So tropical algebra really mirrors positivity. And you know, positive, so you have a positive matrix. There's going to be a dominant positive eigenvector that has a dominant positive eigenvalue, and that's mirrored by this tropical approach. Okay?
Is the determinant the same as like the permanent?
Yes. Yeah. So the determinant of a square matrix is the minimum over n factorial classical sums. It's the solution to the assignment problem. So if you have an n by n matrix, so think about a company that has n jobs and n workers. Okay? And there's a cost, Aij, associated if worker I does job j. In the morning, so in that day, the n jobs to do and the n people to do them. Right? So in the morning, everybody gets assigned a job. So there's n factorial permutations. But you want to do this as cheaply as possible. Right? Over all permutations, you want to minimize A1, pi 1, plus A2, pi 2, blah, blah, blah. That's called the assignment problem. Okay? And the value, the optimal value of the assignment problem is the tropical determinant. Is that clear?
So you mean it's minimum weighted matching problem?
The minimum weighted matching problem, exactly. Yeah, the absolute value. That's called the tropical determinant. Now, of course, the n factorial terms, but there's a polynomial time algorithm, right? So there's an algorithm called the Hungarian assignment algorithm that will do that fast for you, okay? And so maybe you should think about the Hungarian algorithm as a kind of tropicalization of Gaussian elimination, right? Which will do the classical determinant fast. Okay, so before I switch to the next section, let me say one more thing. So some people ask me what should they read if they want to study tropical geometry, or how should this discussion group, continue. Of course, they're phenomenal lecturers like Rainer and Spencer, and occasionally you have nasty exercises having to do with 3 by 3 determinants offered by me. But right now we're all getting ready for the workshop, right? In 10 days we're going to do algebraic geometry and optimization, so maybe we should think a little bit about connections between tropical math, tropical geometry and optimization. So let me introduce 3 of the workshop speakers to you. You can look at their papers. So one is Tran, T-R-A-N. She's going to speak on neuroscience or something. She is the expert on tropical spectral theory. So she's really written some very, very nice papers on eigenvalues and the structure, the combinatorial structure of how the eigenspaces change as A varies. So looking at her tropical stuff would be a good thing to do. There's Yaroslav Shitov, who's amazing. I'll tell you later what he proved. And I scheduled him back to back with June He, who may not need an introduction to this audience. So on Friday, Shitov and He will give tropical lectures. That is to say, 15 days from today. Friday in 2 weeks, tomorrow in 2 weeks. So these are some tropical authors you might like to take a look at. Okay, so how should we draw the image of a matrix? Spencer.
Just a quick question. Is there a tropical version of the Cayley-Hamilton theorem?
Sure. Oh. Yes. If you take the minimal polynomial and you plug in the matrix, you get 0. That works over any semi-ring, actually.
Oh, okay.
Yeah. If you form this polynomial and you plug in the matrix, then, well, whatever 0 means. Okay, you guys figure out what that 0 means. So it's a solution. I mean, the minimum is attained twice since. Okay, let's get to this question. How should we draw? How to draw the image of a matrix? Let's focus on this question. If I give you a matrix, such as this one, how would you draw the image? That's our second topic today. That's tropical convexity. Okay, so let's start afresh. A subset S in R to the n is said to be tropically convex so a subset is tropically convex. Well, if the following holds, suppose you have 2 elements, x and y of S, and 2 scalars, a and b, let's say real numbers. Okay, so you take 2 points in S and real numbers a and b. Then, so whenever you do that, then also the linear combination ax plus by is in S. Okay? So in other words, it's a semi-module. A tropically convex subset of R to the n is simply a sub-semi-module of R to the n. So R to the n is a semi-module over the tropical semi-ring, right? We've done that, right? So you can multiply and add vectors. And if you take a sub-semi-module of R to the n, a set that's closed under tropical addition and tropical scalar multiplication, we're going to call that a tropically convex set. Okay, so our notion of convexity is means just closed under tropical linear combinations. Now, I'm going to identify S with its image in R to the n mod the all 1 vector, and again among friends let's think about this as projective space, right? Because as soon as you have a tropical, suppose you have a non-empty tropical set, right? Suppose it has 1 element, then you can take that element and multiply by any scalar, right? And so as soon, so you know, because S, right? So because, is that clear? So because S classically plus the 1-1 space will be in S, right? As soon as S is non-empty. So as soon as S is a non-empty set, right, any element you can multiply by 7, right? That adds 7 classically to every entry. So when we draw tropically convex sets, we always draw in 1 dimension less. You guys look puzzled. Is that clear? Yeah? So S is a set that's tropically convex. It's closed under adding and scalar multiplication. But scalar multiplication just means shifting by 1, 1, 1, 1, 1. Right? So we might as well mod out by that. Okay? Okay, now certainly the image of a matrix will be tropically convex. Right? It's just the semi-module spanned by the columns. Right? So if I have something that's in the image of a matrix, I have two things in the image of the matrix. Right? So I have, C times something and C times something else. By the distributive law, that's the same as C times something plus something else. Right? So certainly the image of a matrix, whatever it is, will be a tropical convex set. Okay? And these we're going to call tropical polytopes. Okay? So a tropical polytope is the image of a matrix. So a tropical polytope is the tropical convex hull of a finite set of a finite subset. Let's call it V, suggestively for vertices, of R to the n, and we're going to go, mod the 1, 1, 1 vector. Okay, so that's a tropical polytope. So by tropical convex hull of a set, I mean this, as usual, it's the smallest convex set containing the given set. So if I start with a finite collection of points in R to the n, look, I regard them, mod 1, 1, 1, 1. Then the tropical convex hull of that finite set I will call a tropical polytope. So that's the same as the image of a matrix, right? So if I have an n by R matrix, and the image by definition is the tropical convex hull of R points in R to the n, mod 1. Okay? So how are we going to compute these things? How are we going to draw these things? Let's do an example. Let's do an example with n equals 3. Okay, and so let's take the following points in the plane. -2, 1, 1. -2, -2, -2. -1, -1, -2. And 0, 0, 0. Okay? Those four vectors are the row vectors in the matrix C that I erased. Okay, so I had a 4 by 3 matrix, and I asked the question, how should we draw the tropical convex hull of the column vectors? Now I'm going to do something else, seemingly unrelated. Seemingly unrelated. Namely, I'm going to take the convex hull of the row vectors. Right? So rather than taking the convex hull of 3 points in 3 space, instead I'm going to take the convex hull tropically of 4 points in the plane, the row vectors. Okay, and those are the row vectors. Okay, now, well, that set, of course, we're going to do this in the projective plane, right? So we're going to normalize to make the last coordinate 0. So we multiply the first one tropically by -1. So this gives us 3, 0, 0. We multiply this by 2. This gives 0, 0. We multiply this by 2. We get 1, 1, 0. And the last one, these are the same. This point and that point are the same in the projective plane. Okay, so we really only have 3 points. Okay, so we have to take the convex hull, tropical convex hull of 3 points in the plane. We call such a thing a tropical triangle. Okay, we're going to now calculate this tropical triangle. Well, here's what you do. Okay, so let's draw a grid. Okay, So the last coordinate is just homogenizing coordinate. So let's draw these points. So I'm going to draw the origin. Maybe here is the origin. And let me suggestively use 3 colors. Okay, then we have minus 3, 0, 0. That's perhaps over here. And then 1, 1 is over there. Okay. So I have 3 points in the plane. Okay. And I want to take the tropical convex hull. Okay. Well, let's do it pairwise, right? We can certainly, let's start with 2 of the points. So let's just take let's for example take the blue point and the red point. Let's just take the convex hull of this point and that point. That's a one-dimensional polytope. That's called the tropical line segment. And that line segment looks like this. It's this segment. Has a little kink, right? So this line segment is the convex hull of the red point and the blue point. Okay? Now, if that is strange to you, try to think about what it means to be a line in the plane, right? So this is a straight line in the plane. If you have this point on the line and you have that point on the line, well, what should the convex hull be? Well, the convex hull is certainly on the line. The line is a tree, just like in the garden, just like in the tropical garden across from the Expo Bridge. There are lots of trees. And so, the only way the convex hull is this. These are the set of all tropical linear combinations of this point and that point. Okay? Well, likewise, right, so the convex hull of this and this is just this segment, and then, this is this segment. So in this example, it so happens to be the case, that the tropical convex hull, it happens to be also tropically convex. Okay, so this is both classically convex and tropically convex. So it's a classical rectangle, that's a tropical triangle, and that's it. So if you form all tropical linear combination, you take any tropical linear combination of any of these things, you normalize the last coordinate to be 0, it's going to be in there. Okay? This requires practice. You need to do at least 10 examples today, okay, of tropical triangles. Okay. These are, by the way, the generic types. So there are 5 generic types in the plane of tropical triangles. So the one we had here is not a generic type. There was some special, thing going on. But over there are the generic types. So the generic types, a generic tropical triangle. If you pick a red point, a blue point, and a yellow point randomly in the plane, then the tropical triangle, the tropical convex hull, will be a classical polyhedral complex in the plane. That classical polyhedral complex has the F vector 6, 6, 1. That classical polyhedral complex has 6 classical vertices, 6 classical edges, and 1 classical two-dimensional cell. That's a generic behavior. Okay? And these are the possibilities. So for example, you can see it's positioned like this, right? And this is the convex hull, and this is the 2 cell. So there's always 1 2 cell, which I shaded in red, in white. Okay? So these are the 5 types. There are 5 types. For 4 points in the plane, quadrangles in the plane, there are 35 types. There's a picture at the very end of section 3.2 that you can look at. And these are the 5 types of generic triangles. So a tropical triangle in the plane has 3 tropical vertices, colored, but 6 classical vertices. Now, these ones, there are some special tropical polytopes that are both tropically and classically convex. So if you have a set in the plane, or in any dimension, that's both classically and tropically convex, we call that a polytope. It's actually a word, okay? So a polytope is both a classical polytope and a tropical polytope at the same time. So in this case, there's one of these generic types is a polytope. So this is the unique planar generic polytope, and this is a degenerate polytope. This is a polytope. These things are not polytopes because they're not classically convex. Right? They're only tropically convex. Okay, I'm going to throw a theorem at you. I'm going to end the first lecture this morning, the first hour, with the hard theorem. Let me give you a hard theorem. Okay, so the spectral theorems were easy theorems, but here's a harder theorem. Theorem 522. So Noctron is an expert on this too. So she wrote a delightful paper half a year ago on classifying polytopes. Beautiful paper that sort of classifies, combinatorial polytopes in dimension up to 5. Very, very nice paper. Anyway, so 522 says the following. The combinatorial types of tropical convex hulls of R points in n space, or n-1 space. R points in Rn mod R1 are in natural bijection with something else. With some other thing. Okay? Now, what do I mean by combinatorial type? I mean as a classical polyhedral complex. Okay? So these things are all tropical triangles, but as a polyhedral complex, a classical polyhedral complex, they're not isomorphic. Right? So if you draw the face poset, these are not the same. That clear? And these are so I mean as a polyhedral complex. Right? So there are 6 vertices, 6 edges, and 1 two-dimensional face, and with incidence relations. Okay, so they have different face posets. So the combinatorial types of convex hulls, tropical convex hulls of R points in this n-1 dimensional space are natural bijection with a bunch of other things, but in particular with regular polyhedral subdivisions of the product of 2 simplices. High dimensional Toblerone. And we take the simplex, the standard simplex, delta n-1, and the standard simplex, delta r-1. Okay, so I'm going to take a couple minutes to explain this theorem, and then we're going to end the first hour. So, well, what is this? This is the standard simplex with n vertices, right? The probability simplex, if you wish. The convex hull, the unit vector. So this is the n-1 simplex with n vertices. That's a direct product of 2 polytopes. So this is a convex polytope of dimension n plus r-2 with n times r vertices. Think Toblerone. Okay, or if R and N are 3, that's the direct product of 2 triangles. Highly recommended to draw that. Okay. Okay, well, so this thing has subdivisions. So by a polyhedral subdivision, I mean a subdivision into polytopes, and regular means by lying on the floor. Okay, so regular subdivision is one that you get if the lecturer lies on the floor and looks at it from below. Okay, that's a regular polyhedral subdivision. Generically, these are triangulations. Okay, so the generic case are triangulations. So here we have the 5 generic types of tropical triangles. They are the 5 triangulations. These are the 5 supposed to be the the 5 triangulations of the product of 2 triangles. So here R and N are 2. Right? So here, I'm sorry, R and N are 3. N equals R equals 3. So I'm going to explain this in a second. Okay? So if I take the direct product of 2 triangles, I get a nice 3-dimensional polytope with 9 vertices, 15 edges, 18 ridges, and 6 facets. No, 9, 18, 15, 6. Then there are 5 essentially different ways of triangulating this into 6 4-dimensional simplices. But before we get to that, I'd like you to make the following observation. Whatever this is symmetric in N and R. Right? Whatever these things are, this is symmetric. Right? If I take a direct product of 2 simplices, these objects, whatever they are, there's symmetry in N and R. Okay? Now what does this say? This symmetry says if you take the convex hull of R points in n-1 space tropically, it is the same. It is the same as taking the convex hull of R points in n-1 space. If you have a matrix, for example, a 4×3 matrix, the image of that matrix is the same as far as the polyhedral complex goes as that of the transpose, right? The convex hull of the columns of a matrix is the same as the convex hull of the rows. It's a remarkable theorem. Certainly very false classically, but it's true tropically. So tropically, the convex hull. So therefore, that's our eigenspace, right? Earlier we had a 4×3 matrix, but now they're all vertices. Just the role of what's a white vertex and what's a colorful vertex, that changes. There's a rule for transitioning between white vertices and non-white vertices, okay? But other than that, that's our eigenspace. So the matrix we had, I drew the eigenspace, right? Because the convex hull of the 4 column vectors is the same in the plane. 4 row vectors in the plane is the same as the convex hull of the 3 column vectors in 3 space. Okay, so that's the situation. So let's maybe end on this. Well, how are you supposed to take the, how is this a triangulation of a product of 2 triangles? Well, let's suppose the triangle is a red, so this is the dual picture. So if I take this diagram, down here I've drawn the dual graph. Right? So this is a mixed subdivisions, the one so aptly classified by Vissarion last week. So these are the mixed subdivisions of a 3 times regular triangle. Red triangle plus yellow triangle plus blue triangle. I claim that these mixed subdivisions correspond to direct triangulations of the product of 2 triangles. So let's try to think about the direct product of 2 triangles. Right? So, well, how would you draw the Schlegel diagram, right? So the direct product of 2 triangles you can draw, for example, like this, right? So the direct product of 2 triangles has this Schlegel diagram, right? We all know how to draw 4-dimensional polytopes by projecting onto one of the facets, right? So the direct product of 2 triangles is a 4-dimensional polytope whose boundary consists of 6 solid Swiss chocolates. 6 copies of delta 1 times delta 2. That's a Schlegel diagram. This polytope has volume 6, normalized volume 6. N plus R minus 2. Choose N minus 1 or R minus 1. Right? So the binomial coefficient 6 is the normalized volume. That is the degree of the Segre variety. So, and these are the triangulations, right? So how are these triangulations? For example, each of these 6 cells corresponds to a 4-dimensional simplex. So I'm taking this 4-dimensional polytope and dividing it into 6 4-dimensional simplices according to this rule. So for example, this 4-dimensional simplex is the product of a red triangle, a yellow vertex, and a blue. It's the join of a red vertex, a blue vertex, and a yellow vertex. Right? So in this direct product, right? So take the red triangle and take the convex hull of a red triangle, a yellow vertex, and a blue vertex. That gives you 5 vertices, a 4-dimensional simplex. That's this 4-dimensional simplex. This 4-dimensional simplex is the convex hull of 2 red vertices, 2 blue vertices, and 1 yellow vertex. This one is the convex hull of 2 blue vertices, 2 yellow vertices, and 1 red vertex, and so on. And you can see how the duality goes, and I think it's time for a break. Let's take a 4-minute break.